See what happened, and then we can be able to predict or what's likely to happen in the future. Which is very important in this business, of course, because we have to keep this for 100,000 years safe and well. So that's why we are doing it. But how we are doing it, I'll tell more about that. We need to know the uncertainties, and from the safety assessment, you had some lecture about safety assessment, I think. From the safety assessment, the most important uncertainties were the distribution and frequency of water-bearing fractures, the stress magnitude, distribution of deformation zones that can impact on the layout, and the distribution of amphibolite. I'm going to talk about these things because they are linked together. So, this is actually a safety assessment, analysis for long-term safety. Have you seen this? No. What we do, we have to gather knowledge about the rock at the site, and we have to find out what processes affect the final repository during time. With this knowledge, we analyze conditions over time, what's happening, and then we make up scenarios, what can go wrong, and what could be the consequences if it goes wrong. Is it understandable? Yes. So from that, we build up something called safety functions. Did Peter talked about safety functions? Yeah. That's actually what exactly is important. So one safety function could be the amount of water allowed in the repository. Examples like this. Okay. And for this reason, to gather the knowledge, we investigate and we make models, different type of models. As you know, I'm not going through this model, but this image, but I'm only going to talk, or this session in the morning is going to be about the rock. So, to find a site, first of all, you need some ideas what is important. So, ideas about the safety functions. This is the safety related to the site characteristics, the bedrock composition and structure, rock mechanical conditions. Do you know what rock mechanics is? Rock mechanic people, geologists, they find out how the rock was created, the geological evolution, etc., etc. A rock mechanic, those people, they count, they calculate the rock strength, the maximum stress in the rock, and so on. So they are more engineering people. We are more academic people, so to say. Then, very important thing is also the groundwater flow, the groundwater composition, retardation. And with retardation, I mean that radionuclides which escape for some reason, one of scenario, they can escape. And the groundwater is bearing them up to the surface. So the fractures they are going through some minerals can retard or even vad heter
vad säger du på svenska?
Att fastna på.
Att de stick.
They can stick to fractures. So this is the retardation, which is important. And of course the overall understanding. And for this different important characteristics, we make models. And this you maybe have seen. SKB has worked for more than 30 years with these issues, and from the beginning they started to look at certain places, but they have decided how it should look like, and they started with it. And when you start with an expectation, it's not very good because you are biased, as you know. So the next study during the 90s was more to look at environment for which is proper than a strict rock type. And after these studies, there were chosen some places to investigate and so on. So what happens during those years, it was that the understanding of the rock and processes increased, of course. As you know, Forsmark has been chosen to be the siting place for the repository. An application was given 2011. But not only at the surface work was done. So in details, concepts were tested already during the 70s in an old mine. So before Esper Hard Rock Laboratory was built, SKB had the opportunity to make tests in an old mine. Then, early 90s, the Esper laboratory was built. So all research, demonstration, training, and so on is done there. And when we talk about site investigation, it's not only the rock we have looked at. We have looked at the sea, the animal life, cultural environment, the plant life. So if you have heard the term site descriptive model, it concludes everything from the rock, from the water in the rock. So it's a singular site descriptive model, but it's compound of different disciplines. And we worked integrated interdisciplinary during the site investigations, which was very important. And I hope all of us this morning will show this. But I'm going to talk about geology, of course. And it was investigations on the surface, geological survey. It was drilling to take cores from the ground, measurements in the different type of measurements in the drill cores and the boreholes. And then we had an aerial geophysical measurement done, or several measurements. And this altogether was finalized in different models. And you use different models, and now I'm talking about the geological models for certain purposes. For example, this is the rock domain model. This model tells about the properties of the rock. This model over there, same volume, same rock volume as this. This is a deformation zone model. So it shows the unconformities in the bedrock. Why are deformation zones important then? Can anyone guess? What is a deformation zone? It's actually a fracture. The rock is fractured. So an earthquake creates a deformation zone. So the rock is sheared, and when you shear a rock, then you get openings, and water can go through, which is important for our case, to see where the water is and so on. So the deformation zone model is important to describe the unconformities in the rock and to give an idea for the hydrogeologist, hydrochemist, where the water is. But we also have, with these two models we have described the rock and the deformation zones. But there might be water also in the fractures between the deformation zones. What's happening here? Those two models are deterministically modeled. And by this I mean that you actually observe on the surface that there is a deformation zone, the rock is fractured. On the sides it's not fractured. We drill, we see a borehole section where the rock is crushed. So this model is made deterministically, saying that by direct observations of the rock. But it's not possible, as you can imagine, to make a deterministic model of the fractures between the deformation zones. For this case, a fracture could be 1 meter long or 20 or 150 meters long. In that case, we have to drill a lot. So this model is made, is a statistical model. And it's a special modeling methodology called DFN, Discrete Fracture Network. So it's a lot of realizations made to get the most possible appearance of the fractures. And what it shows, it's both directions of the fractures and the length. As you see, there are different lengths of the fractures, which is important when the hydrogeologists put their properties in the rock. Is it understandable? So, how does Forsmark site look like geologically, and how does it meet the requirements from the safety assessment, the safety functions? This is a very short description, of course, of the site. For interested people, maybe you know that all our models, all our investigations made are published, so anyone can download them from our website. And TR0805 is the site descriptive model for Forsmark. So, what about the geology? It's a homogeneous bedrock. It's a granite. I saw that Tommy had a picture here. Remember this one? So the granite, oh, actually it's not, yeah. The granite is a feldspar-rich, quartz-rich rock, which is very important because it's a rock type which is good to transport heat. So as the canisters are going to be hot when they're deposited, they can be up to 100 degrees hot. Then if you deposit a hot stuff in a rock, what happens? Have you been making up fire on an outcrop? What happens then with a rock? Have you been outside making up fire on an outcrop?
That's illegal.
But you have done it.
I know it will crack.
Yep. It cracks. So it's a thermal load on the rock and it cracks. So if it cracks, what happens then? You get fractures, of course. And if you have water, you start to have a water flow through, which we don't want. So the granite is good because the thermal properties are good. It's cooling down, it's transporting the heat out. If we have had a rock type which is with less quartz or no quartz at all, then it's insulating, not transporting heat. So we are actually putting a thermal load, which is not good for the repository. So we have granite, we have steep and gently dipping deformation zones. So they are steep. This is steep deformation zone. This is a gently dipping deformation zone. It's a very good thing to have the steeply dipping deformation zones, because imagine that we have tunnels like this, and we are not allowed to deposit in deformation zones. No canister positions in deformation zones. So then if the deformation zone is vertical or subvertical, then we can deposit on those sides. If the deformation zone is shallow dipping, gently or shallow dipping like this one, then it's crossing like this. So a lot of space goes away, not very economic. Then you have to build a bigger repository. One example of this. Have talked about the thermal conductivity. Then what about the rock mechanics? Actually, it's relatively high in situ stress, meaning that if you're down there measuring the stress, it's higher than a normal bedrock, Swedish bedrock. This means that together with the thermal conductivity, coupled to the thermal properties, if you elevate the temperature and have a high stress, then it fractures easier than you have a low stress. Is it okay? Understandable?
So that high in situ stress is not that good?
It's not good in that sense, but it's good in another sense. It's always like this. Looking at the hydrogeology, the upper part of the bedrock is highly fractured, a lot of water-bearing fractures. You see, I'm going through this more in detail, but you see there is a blue part on the top. This is the top of the model, this is the bottom. On the top it's a blue one and it's a green one over there. The repository is going to be placed down here in this grayish, whatever, brownish part. This is the one fracture domain called, this is fracture domain 2, fracture domain 1. So the highly fractured water-bearing, the surface is highly fractured, or the rock up close to the surface is very highly fractured. But where we are going to put the repository, it's partially fractured, almost no water-bearing fractures. And this is actually the result of this. Can someone think about it? We have high stress down here, no fractures. We have water-bearing, a lot of fractures on the top. It's not that easy, maybe.
What's the question?
Can you say what the linkage between the sparsely fractured water-bearing, the sparsely fractured rock at the depth, the linkage between that and the high in situ stress?
Probably like on the surface, like after the ice age, there's a permafrost, so it created a lot of fractures on the surface, but at the bottom, the water could not penetrate that deep enough, so that there's not that much expansion into the rocks.
Yeah, it could be that, but imagine that you have an ice cube and you're pressing it. You're pressing it just before burst. Then you are increasing the stress. When you press just a little more, it fractures, and then you release the stress. Do you understand? And so, why is it? Where is the point? Where did I put it? Why is it then fractured up here and not here? It's what you said about the ice sheet. We have had 2 kilometers of ice 10,000 years ago up here. No living, no dinosaurs. They were dead before that. So 10,000 years it was 2 kilometers of ice sheet, which is quite heavy. So the bedrock was pressed several hundred meters below where it is today. The ice sheet came very slowly, so the down pressure was slowly done. The rock was almost in equilibrium concerning the horizontal stress. Horizontal stresses, there are two vectors, and vertical stress in equilibrium, like this. Then it stayed there for a while, and when the ice sheet got away, it happened very rapidly. So meaning that the stress release from the top, the horizontal, the vertical stress was taken away very quickly, which means that the difference, which means that if you are a small cube of rock and you are sitting there, suddenly something happens. You're going up, popping up, and the top of the rock was fractured. So typical fracturing here up here is horizontal, meaning that fracture release is the vertical fracture release was vertical, of course. Is it understandable? Okay. So I'm going to talk about something about the deformation zones, the significance and influence of the zones. Can you see the images over there? Is it easy to you to see in the back? Can you see what's happening up here? Because I'm going to. Can you see that this rock is gneissic? You see bands over here, black and white bands. This we call ductile deformation. So when this was deformed, it was quite hot. So no fracture, it's hot, it's plastic, it's ductile. This type of zones are harmless for our purposes because there are no fractures. So undeformed rock and ductilely deformed rock, the hydro properties are the same. It's tight. Up here you see a reddish rock with some something which is whitish. You see that, for example, this is a piece of rock which is surrounded by something which is whitish. It's quartz. This rock has been brittly deformed. And it has been sealed, the fractures has been sealed with quartz. But parts of this, you might have still not sealed parts, and there are canals for water. So what we are interested in is the brittle deformations, the zones. So what we do is actually we are mapping the surface, mapping the zones. We also drill. We map the cores, and we also have another technique to help us. This is a core. You're going to see cores next week. This is a core. This is image of the borehole walls. So we have a special equipment. So we go into the borehole and film the whole borehole. We're filming it. And then we can wrap up the image. So what we are seeing is that kind. The hole is actually wrapped up. Downside of the hole, left and right. And what we see here is actually a cavity in the deformation zone. So that's used for the modeling. And this is also very important for the knowledge, for the understanding of how the water goes, as Manu is going to talk about later on. So where are we geologically and why? You see Sweden. Forsmark is up here. Laxemar is, or Oskarshamn is here. This is a geological map. And this is a aeromagnetic map. So with airplane that has been flown 200 meters between the profiles, and then this map has been compiled. This is a so-called geophysical method. And geophysicists are those people who are using different kinds of physical properties to tell us, geologists, how it looks like beneath the overburdened earth, houses, lakes, whatever. And it is very helpful, because what we see, you see there are certain structures here that tell us something. This is a close-up of Forsmark. And what you see the blue streaks, or pattern of blue and red and yellow and purple and white. The blue parts, it's very low magnetic response. So no magnetic, almost no magnetic material at all. The highest magnetic material has this. So the blue is lowest, the reddish and whitish is the highest, and everything in between. So how does this happen? Every rock, almost every rock, has a portion of magnetic mineral called magnetite. It's an iron oxide. And it's sitting in the rock evenly, more or less evenly distributed in the rock. If you shear the rock, you open up, fluids come in, and then the iron of the magnetite, which is an iron oxide, oxidizes and turns to a mineral called hematite. And a hematite is non-magnetic. So you see, this is extremely important tool for us to trace the deformation zones without seeing them. We can observe in certain places where we have outcrops, or we can even dig a hole and look at the bedrock. But then we correlate with a magnetic map. So it's extremely important tool. So what we see is, you see this bluish thing. I should say also that this part, you see it's a very good resolution, which differs from this resolution. This is a more detailed, this is flown by helicopter with a spacing of 10 meters. This is aeroplane flown magnetic measurements, 200 meters. So what we see, you see this very prominent line here, continues to like this and down there, continues up here. This very prominent line, it continues like this, probably somewhere. This prominent line, it's very straight. See it here? This is actually the border of something called a tectonic lens. And we are, the sighting of the repository is inside on the top of the tectonic lens. If you have some imagination, you can see that it goes up like this and back and going down like this and turns again. So this one is the Forsmark tectonic lens. And what is a tectonic? Yeah?
What kind of depth can be resolved with this method? To what depth does it
very good question. It's not very deep. Tens or maybe up to 100 meters. It depends, but it depends of the spacing, of course, between the measurement points, because they're measuring, flying measuring continuously, but the spacing between the profiles is 200 meters. So, but you can, if you have a ground magnetic map, you can walk profiles which are spaced 5 meters and measure each and every meter. Then you can go deeper and more detail. In that case, it can go down to several hundred meters.
But the depository is far more deeper.
500 meters.
Okay, so that's like the map of the surface.
What
the fractures look at the surface like?
More or less, but then more or less of the surface, some 100 meters down. But the knowledge about deformation zones and their style tells us that they are going deeper. And this is just the first information given. So a tectonic lens is a rock which is surrounded, enveloped by deformation zones. Simply said. So, how do we process data? I haven't talked about much. I have talked about the models and certain things, but how do we process that? How do we make those models? First of all, this is an outcrop mapping. So the outcrop mapping together with a aeromagnetic map, geophysical aeromagnetic map, we make, this is actually the mapping, the bedrock mapping, the ground surface. Can you recognize some of the rocks? Can you say what type of rock? I mean, from, remember what Tommy said? What could this be? A granite, maybe? Yeah. This is actually the granite. This is the Forsmark granite. This is some type of gneiss. You see here, this is a granite, and there are blobs of something dark. This is amphibolite. So the granite is a silicic rock, high quartz content, the good rock for thermal properties. This is more mafic rock, no quartz, not very good. Yeah.
So is that intrusive, or was that deposited by fluid?
This one is intrusive.
Oh.
So the granite was there, and then the mafic rock came in. Both are intrusive, but they're different generations of intrusions and also magma composition. So we gather data in field, and for this we use those tools, only those tools, nothing else. Then we make a map of the bedrock. And you see the tectonic lens is here, the granite here. We call this for a 2D model. Actually, the important thing is to remember that even the mapping is a model. So, depending on your experience as a geologist, you make an interpretation. You decide, you assume certain things. So what you're doing is not data which is accurate. It's no measurement. It's a judgment. So the mapping is actually a model. Doing this model, the 2D model, you need to know how it is mapped, what uncertainties is there, was the geologist skilled or not, etc., etc. Because otherwise, if the mapping was done with less experienced geologists or whatever, or different background, then it's going to be in this map. So it's very important to have the uncertainties and the assumptions made by the mapping geologist. You see the red streaks over here. This is drill sites and boreholes. So after the 2D model has been created, we decide where to put drill holes. And there it comes. Because we know that there is a deformation zone from the magnetics. We have maybe 1 or 2 outcrops already mapped. Then we try, how deep does it go? And what properties does the properties differ from the surface at depth and so on. So we drill. And this is a typical drilling machine. You see the rod. This is a drill bit. So what's happening actually, this is cutting the rock. So in the middle, the core is a piece of cylindric sample is taken, so to say. This is the core. So you drill and you get up samples from the rock.
Just a question.
Yeah.
How deep can you go using this technique?
Normally, our holes were 1,000 meters, subvertical, 1,000 meters. The deepest hole SKB has drilled is 1,700 meters with this technique. But normally about 1,000 meters. So exploration, ore exploration and so on, they typically does between 500 and 1,000 meters. So it's a common technique. When we get typical geologists working with hand lens. So when the cores are up, then we map them. And we have a special method called bore map. You remember that we make we film, we make a movie of the borehole wall. And so the core, together with the movie from the borehole, we use in this bore map method to log the core. So what we see if we see a fracture in the core, if the fracture is non-coherent, is detached, you have two pieces. You don't know whether the space in the hole is 5 centimeters or 1 meter or just 2 millimeters. You don't know because it's detached. You cannot say anything. But it's very important for us to know, for the hydrogeologists and for different people. So therefore, we need this image. And you see here that here is a fracture. This fracture is identified by the geologist there. And then we can measure the orientation of the fracture and the aperture of the fracture. And this particular information is extremely important for the statistical modelers, the DFN modeling group, because they take the statistics, the orientations, to feed their models, to get this deformation zone, fracture zone model. After that, the hole is logged. Then we make up those kind of diagrams. We call them 1D models because it's 1D. We have a line. By the way, the core is 76 millimeters in diameter. So on this side here, this is the rock. On this side here, this is the fractures in the rock, in the core. So what we have here is the depth. You see it's from 0 down to 1,000 meters. Don't bother about this depth, because this depth tells us that where this is along the borehole, this is the actual depth, because it's slightly inclined, it differs. So here we have the rock type. Here we have alteration. And why is this important? This type of alteration is actually oxidation. The low magnetic parts. You remember that hematite, magnetite in the rock during fracturing turns to hematite, and it appears as an oxidation, red staining of the rock. On this side we have fracture frequency of sealed fractures. Those fractures are sealed, they are not open. No water can go through them. This is the fracture frequency of open fractures. So what we make is, looking at this part, you see it's a lot of rock types. You have to conceptualize. So we divide this in rock units with typical characteristics. And on this side, we look at the fracture frequency, we look at the oxidation, and we decide that this has to be a deformation zone. So, after this exercise, we look at each and every borehole, and we make a 3D model. So this is a rock domain model. The repository is going to be placed in this place, so this is taken away. So there are two rock domains which are 29, which is this one, and 45, which is this one, which meets the requirements for the repository. The rest is not fitted, it doesn't meet. Okay, I talked about this red staining oxidation. There is the image of that. You see, there is a fracture, and around the fracture, it's reddish. So this is where the fluids have been flown and altered the the rock. Can you see which drill hole shows a deformation zone and which is more fresh rock?
B is fresh.
Sorry?
B is fresh and D is deformation.
Yeah. How could it, how do you?
The color.
Yeah.
D to
Yeah.
is reddish.
He said that B is fresh and D is deformation zone. And you took the color as a sign, yeah. Because it's a lot of fractures, so the whole, all cores are red stained. And you also might see that there is a crush. The rock is crushed, so it's not coherent. One of the important things to tell the story, to say what has been been going on during the past years, is the fracture minerals. Because depending what fracture feeling you have, it tells you when it has been deposited. And we have a different stages of different activations of the fractures. So what a lot of studies has been done on fracture minerals, composition, appearance, combination of different minerals, etc., etc. And there is, for example, different fracture minerals plotted according to this is the frequency of the mineral, it's clay mineral, and this is the depth along the borehole. So what we see is that we have a lot of clay minerals up here, some here, and not very much overall. For example, this mineral, it's all over the place. And what this tells us a lot. This is a clay mineral. Clay mineral is actually not formed originally. It is transformed from something different. It's a weathered product. But to weather something, you need water. So what this says that those minerals, there has been water in these fractures. And I mean, at this depth, this is probably a deformation zone. This also. But down to 40 meters, how come this? How come there is clay minerals on the top, close to the surface? Think about the fracture domains. Think about the upper fracture frequency in the upper part.
In upper part, there are a lot of fracture.
Yeah.
So you said the clay mineral is kind of evidence for fracture. So.
Evidence for water. Yeah. And we have a lot of water on the top in this highly fractured volume. So therefore we have the clay minerals. I think I skipped that. Oh, I think I go here. We're talking about these deformation zones. They have a typical oxidation zones. We can see them in geophysics. We can see them in boreholes, etc., etc. We can model them deterministically. You see these fractures here, horizontal. subhorizontal. If we closely look, this is grayish rock, no oxidation. This is the sheet joints, these stress relief fractures. This is part of the upper part of the rock. And you see it's could be quite wide fractures. And this is also shown here. The highly frequency of subhorizontal fractures open in the uppermost part. It's grayish, but you see a lot of open fractures. Remember that the borehole is drilled horizontally, subhorizontally. So you see the fractures are like this. So, and this is the abundant, shown from the deformation zone deeper down. See the oxidation and the fracturing, of course, deformation. So what I'm actually talking about, I'm talking about two processes. One old process, creating the fractures, the deformation zones, and one very recent process, which has been after the Ice Age. And this is very important for us to know, of course, because we won't expect this kind of situation even after an Ice Age that deep as 500 meters beneath the at the repository level. So no worries about this highly fractured even after an Ice Age or several Ice Ages, because it's too deep to get this process work. Okay, so I have talked mostly of observations done and conceptualization by model, by theories applied on this concept, different concepts. I mean, the oxidation contra non-oxidation. It's purely observations. But we also use analytical methods. And this shows actually absolute age determinations of rock minerals and a cooling story. We have a relative age determinations by, as someone said, is this intrusive? We saw the granite in the previous picture. We saw some black amphibolitic types. That tells us that the granite was there first, the amphibolite came after. You know, it was a very important discovery in the early 90s or late 80s that a rock which lies below another rock is older than the rock above. They were talking about sediments. But this is very good knowledge to know that what has been sedimented below is older than that what was sedimented above. So using relative age determinations is field methods. But we have also laboratory methods, which tells us even more. Because we can see that, for example, in the fractures, there are different fracture mineralogies. We can determine that the fracture which is closest to the rock is first generation, maybe. Second, growing on the side of this first generation is second generation, etc., etc. So we can make up this kind of relative age determinations of the fractures. But we can also determine them with absolute. This is a very complicated diagram. What I want to point out is that the formation of the rock is 189 to 185 billion years ago. And how did we come up with this? Yes, we take a mineral, a zircon. A zircon has a portion of uranium in it. So when the zircon was formed, from melt to when it crystallized, uranium was trapped in the zircon. And then a half decay started, of course. By taking out the zircons today and look at the proportion of uranium and lead, which is the lead 2006, then we can tell how old it is. So it's a very, I mean, this is your business, you can much more than me about that, but that technique is extremely useful. And by using the isotopes, radioactive isotopes in different minerals and different radioactive isotopes, we can tell a story about the cooling. We can tell a story about when a certain fracturing appeared, more exactly than the relative. And so knowing that amphibolite forms at 500 degrees, we make an age determination of this. So we have then both the temperature when it was formed, so the actual happening, and the age when it happened. Yeah. So, summarizing everything. As I said, I only talked about geology, almost entirely geology. But there are hydrogeochemistry, hydrogeology, rock mechanics, etc., etc. They took the geological model and used it as a framework for their purposes. So at the formation zone, we provided the formation zone with certain properties, and then a hydrogeologist put in the water where we said probably here is water content or whatever. The rock mechanics took our model with the different rock types and also the formation zones, and they applied their modeling techniques on it. The hydrochemist the same, etc., etc. And notice, I love this picture because here's the geological model. You see this, you remember this, the upper part of the rock, the surface part. Our determination was that it's about 50 meters on this in the northwest and about 200 meters down here. Our model shows that from our data. The rock mechanic, when they made the rock mechanic stress models, horizontal stress models, it shows that the blue one is very released rock, very low stress. This is slightly higher and increases down to the depth. So you see the same pattern as here. So the theory is okay. This is a DFN model for hydrogeology, discrete fracture network model for hydrogeology. You see the same pattern. Water up here, not very much water down there. This is the conceptual distribution of model end members of water, so different water types. Same trend, very close to the hydrogeology, of course. So this understanding has to be common, and if it's common, then we think we have come quite close to the truth. So, keep asking. Yeah.